In radiology departments, doctors analyze large volumes of CT scans every day. Relatively straightforward tasks are often performed manually and take considerable time. It makes sense for clinics to automate parts of this process. For example, automatically segment the spleen in a CT scan, calculate its volume, and pass the result downstream into a radiology report pipeline. This kind of automation is well within the reach of modern medical AI. But here is the practical problem. Medical images contain sensitive patient data. Sending such scans to external AI services is often prohibited by privacy regulations. And even where it is technically permissible, many healthcare organizations are unwilling to accept the risks. The usual answer to this problem is to keep everything on-prem. But on-premises infrastructure is expensive, hard to scale, and doesn't readily support the elastic compute that AI workloads often require, especially when GPUs are involved. SuperSwarm offers a different path. As a quick recap, SuperSwarm is a confidential cloud that runs across existing infrastructure, public clouds, on-premise servers, or a hybrid of both. Every workload runs inside hardware-protected, trusted execution environments. This means the model, the data, and the runtime state remain isolated from everyone, including the infrastructure provider and the platform operator. And crucially, that confidentiality is cryptographically verifiable by any external party at any time. In this demo, we show how a model from the MONAI Model Zoo can be deployed as part of a medical AI application on SuperSwarm. The model runs inside a confidential execution environment. Patient data stays protected throughout, and confidentiality can be independently verified. For this demonstration, we are using a tutorial project from the MONAI ecosystem. MONAI stands for the Medical Open Network for AI. It is an open-source framework for medical imaging AI, co-founded by NVIDIA and backed by leading academic medical centers worldwide. It has become the de facto standard for medical imaging AI research, and NVIDIA continues to back it as part of its enterprise AI platform. The Fast API application we are going to deploy on SuperSwarm takes a CT scan as input, segments the spleen, calculates its volume and area, and returns the segmentation mask alongside a visual overlay. Such a focused AI microservice may fit naturally into a larger radiology pipeline. We prepared a deployment script for SuperSwarm. We also added a UI for uploading studies to the original example app. Let's deploy it. First, we log into SuperSwarm and create a new cluster. We give it a name, attach a GPU to support the AI workload, and leave the other parameters at their defaults. Once the cluster is created, we export the qconfig and run the deployment script. The script goes through all the necessary stages automatically. SuperSwarm detects the deployment and creates two public domains, one for the web UI and one for the API. Before the application becomes accessible, we need to verify domain ownership by adding the corresponding DNS records in Cloudflare. This part is trivial, so let's skip it. Fast forward, the records are added and both domains are verified. There is one final step, publishing the cluster. When we publish, SuperSwarm freezes the runtime configuration and generates deployment evidence, a cryptographically signed snapshot of the entire runtime configuration. More about that in a bit. With the cluster published, let's open the application. For this demonstration, we have a CT scan available via a link. We paste that URL and press Run Segmentation. The model processes the scan and returns the results. We can see the calculated spleen volume and area, the segmented image, the segmentation mask, and a visual overlay showing the overlap. The mask can also be downloaded directly for use in downstream steps. The entire computation happened inside the confidential cluster. The CT scan was processed within the TEE, and only the results were returned to the UI. The deployment can be verified using a special browser extension with the deployment evidence. It confirms whether a site is deployed in Swarm and shows the full deployment details. Let's walk through that now. Here we can see the domain, the certificates, the namespace, and the full structure of the deployed application. Each component can be expanded to inspect its individual configuration, image hashes, environment settings, and everything else that influences how the application runs. The deployment evidence includes the certificate fingerprint for the application's public hostname. We compare it against the certificate shown in the browser for our application. They match. This confirms three things together. The application is running in the configuration shown in the evidence, it is running inside a confidential environment, and it is using this specific certificate. The certificate is cryptographically bound to the deployment, and no other configuration could produce it. Anyone can perform this check independently, at any time, without relying on Super Protocol or any other third party. What you have just seen is a practical example of a medical AI application running on confidential infrastructure. The segmentation model from MONAI Model Zoo is deployed as a standard container inside a superswarm cluster. The patient data never leaves the confidential environment during processing. The runtime is hardware isolated, and the deployment is cryptographically verifiable. This demonstrates something important for healthcare organizations. With SuperSwarm, hospitals and research teams can deploy their own AI applications and retain full control over their data and their execution environment, even when running in the cloud. The confidentiality guarantees do not depend on trusting the infrastructure provider. They are enforced by hardware and verified by cryptography. Super Protocol, making self-sovereign computing accessible.